Okay, so we're studying Half-Life, and if you watch the introduction video to Half-Life, then you know that Half-Life is how quickly it takes for a radioactive isotope to break down into a stable substance. So here we're going to demonstrate that. So right here I have a sample, which is all of the red chips, a sample of Garfieldium. Garfieldium is an imaginary radioactive isotope, and this sample is made up of 16 atoms, 16 radioactive atoms. Okay, they are going to break down in half. Their half-life is 30 seconds. So that means every 30 seconds, half of these radioactive atoms of Garfieldium will decay into a stable substance. So when you're looking to calculate half-life and to see how it works, the best thing to do is to create a little table, okay, so that you can track the rate of decay in your table. And so in my table here, I've got 3 columns. I've got the half-lives. I'm going to keep track of the number of half-lives that go by, the amount of radioactive material that's left, that's still radioactive after each half-life, and the amount of decayed material that now exists, or it's the stable compound, so the amount of decayed stable material that now exists after each half-life. Okay, so remember, Garfieldium breaks down in half. Half of it becomes stable every 30 seconds. Okay, so let's start this out. Let's say 30 seconds have gone by. So now that 30 seconds has gone by, we have 1 half-life has passed. Okay, and that means that half of these radioactive isotopes of our sample of Garfieldium are now stable. So they are now stable. So now, after 1 half-life, after 30 seconds, we now have 8 atoms that are still radioactive, and we have 8 atoms in our sample that are now stable. They have decayed. They are considered to be what they call daughter product, and they are stable. A radioactive, our parent product. All right, so now another 30 seconds has gone by. So that means half of our radioactive isotopes are now stable. So since we had 8 of them, that means that 4 of them, half, have now become stable. So now, after our second half-life, which is now basically 1 minute has passed, since each half-life is 30 seconds. There was 30 seconds. Now we're up to a minute. Okay, now we are now down to 4, after our second half-life, 4 radioactive isotopes remain. And now we are up to 12 daughter product, or daughter atoms, or stable atoms. Okay, so now we're up to 12. Okay, and now another 30 seconds goes by. So now we are at 3 half-lives. So now we are now 1 minute and 30 seconds into the breakdown of our Garfieldium sample. And so after 3 half-lives, now we lose half of the radioactive substances that still remain. So that means 2 of those atoms are now stable. So now we are down to 2 radioactive atoms, and we are now up to 14 stable atoms. Okay? And now another 30 seconds has gone by. So now we're talking 2 minutes, and we are down to now half of these remain. So half of our 2 atoms has now become stable. So now we are down to 1 radioactive atom left, and we are up to 15 stable atoms. Okay, and now after another 30 seconds, if we could do it, we would split this one in half, and then we would keep splitting the pieces down until all 16 atoms have become stable. And then our Garfieldium basically would no longer exist. It would have decayed into another compound that was stable. Okay, so that is half-life or radioactive decay. That's how it works. It always depends on the substance and what the substance's half-life is. So this was 30 seconds was the half-life of Garfieldium. So that means every 30 seconds, half of the radioactives that we had would decay into a stable form. Okay, so our decayed matter increases, our radioactive matter decreases, and you can see how much time has passed every 30 seconds. So 30 seconds, 1 minute, 1 minute 30, 2 minutes. So after 2 minutes, our Garfieldium sample was almost all the way decayed away. It was all the way down to 1 atom. And we continued to do that until our Garfieldium no longer exists. It had converted all the way over into a stable material. All right, so I will do another video to show you how we graph that. So watch that next video, and if you have any questions about this, please feel free to ask. Thanks. Okay, so in this video I'm going to show you guys how to calculate a half-life problem. So here's a sample problem. The half-life of Clovarium-131, which is an imaginary element, is 8 days. So how many grams of a 777 gram sample will remain after 40 days have passed? Alright, so in order to calculate this and figure out how many grams of this Clovarium that we have at the end of 40 days, first thing you need to do is figure out how many half-lives that's going to be if each half-life is 8 days. So 40 divided by 8 is 5. So that means 5 half-lives of this radioactive isotope will have to have passed in order to get to 40 days. So all we need to do is make ourselves a little table here. And you'll want to always do this when you're calculating a half-life problem. And we put down at 0 half-lives, we start out with 777 grams of the radioactive material, the Clovarium-131, and we have 0 grams of the decayed stable product that's produced when the radioactive isotope breaks down. So after 1 half-life, we put 1 half-life in here, which is 8 days. If we divide 777 grams in half, or by 2, we end up with 388.5 grams, and that means we're going to have 388.5 of the decayed as well, because half of it stayed radioactive, half of it decayed into a stable element. Okay, then after 2 half-lives, if we divide 388.5 in half, we end up with 194.25. And so that means we split that in half. That means half of that also goes over here on this side, because now we've added half of this material to the stable side. So we add 194.25 to the 388.5 that we have over here, and we have 582.75 grams. Okay, now we go to 3 half-lives, and if we divide this in half, we end up with 97.12 grams. And then we add that to the other side, and that would be 679.88. Okay, and then we go to our 4th half-life. We divide this in half, and we're at 48.6 grams, and we add half of that to the other side. We're at 728.48. And then our last half-life, which would be 40 days, because remember each half-life is 8 days, so 8 times 5, that's our 40 days. And this is where we're supposed to stop. We divide that in half, we end up with 24.3, and we add that to the other side, we have 752.78. So to answer our question, how many grams of the 777 gram sample will remain after 40 days? Our answer is 24.3 grams would remain of the radioactive clavarium-131. So whenever you calculate these problems, always make sure you create a little data table here. It will help you figure out how much is left after so many half-lives have passed. Okay, so if you have any questions, please ask Mr. Mallicoat. Thanks.